Hello students, the continuation of electric charges and fields. Students will be able to understand the electric fields and the fields pattern and their application. And also they can easily demonstrate about the electric dipole and its application. Let us see in detail. Electric field. See, the electric field is a region of space around the charge or a system of charges. And the SI unit of electric field, which is Newton per Coulomb. Now, the electric field intensity. The electric field intensity, which is nothing but we can say electric field strength. So, the electric field strength extends up to infinite. But in practicals, we can say limits up to some certain distance. So, we can say the electric field strength of at a point, the electric field is the point of electrostatic force per unit charge. So, we can say that as a mathematically electric field denoted by E vector. So, E vector which is equal to limit del turns to 0 F vector by Q naught. Okay. Next one is electric field lines. See, actually the electric field lines or lines of forces or the imaginary lines. See, these are all that curved path or maybe the straight path along the unit positive charge. It is supposed to move when it is free to do so, that in the electric field. See, the electric lines of forces do not physically that appears. It exists in a imaginary lines, right? And the properties of electric field lines, it always starts from positive and ends with negative. And there is no two electric field lines are intersect each other. Because why it is? Because of no two direction is possible for the charge to move, right? So, unidirection is possible, so that there is no two, the charges are getting interacted. Now, we will see the field lines due to the point charge. If suppose the Q is greater than 0, see the diagram on the screen. The arrow mark which is outward, that means the direction of the point charge which is radially outward. So, that is also spherically symmetric in nature and it is outward direction. See the second diagram, that is Q is less than 0. So, Q which is less than 0, which means that is a negative point charge and it is also spherically symmetric but inward. So, inward which means what? It starts from infinite, right, ends with the point, so it is reaches to the point. And the third diagram you may see that is for the electric lines of forces due to a uniform field. So, the electric lines of forces which is parallel, see the lines which are going on parallel to that, and the conductor which is so they equally and spaced, equispaced we can say that, and it is indicating that the electric field is uniform at all the points, right. So, that this is the electric lines of forces uniform nature. And the next one is the electric lines of forces to a pair of equal and unlike charges, that is dipole. See the dipole which is separated on that screen, how it is, the electric lines of forces moving, the direction with the arrow mark you have to check it. And the next diagram which is for the electric lines of forces due to the pair equal and like charges. So, it may be you have taken positive charges or maybe two negative charges, right. So, that is the next diagram which we have seen. The next one is the electric lines of forces are closer, means what will happen, that is the electric field will be very stronger. If suppose it is too crowded, which means what, electric lines of forces it is very stronger. You may see the two different diagram. The one is very crowded in nature of the electric lines of forces and another one is it has a little space. So, if you are drawing like that, it is stronger. The diagram Q says that stronger lines of forces, that S which says that it is not that much of stronger electric field it contains, right. So, the next one is electric lines of forces are parallel lengthwise and perpendicular to the surface of the conductor. That means what? They are equispaced and it is indicating that the electric field is uniform at all the points, right. The next one is electric lines of forces contracts lengthwise and represent attraction between the two unlike charges. So, that is showing through the diagram. See that lengthwise it is getting contracted because of why? Because of it is representing the attraction next to that adjacent, all the charges are giving the attraction towards the, because of the unlike charges. Now, let us see electric dipole. What is electric dipole? See, the electric dipole is the pair of equal and opposite charges separated at a distance. See, electric field produced by an electric dipole, which we can say that the dipole field. Electric dipole moment, which is we can denote it by letter P, and that quantity which is the vector quantity, and it is measuring, it helps to measure the strength of the electric dipole. So, we can say the electric dipole moment P vector, which is equal to Q into 2L. So, that is we can say that the pair of equal and opposite charges separated at a distance. That is only you are seeing on the screen the diagram. That is the dipole minus Q plus Q, the opposite, equal and opposite charges separated at a distance. Distance we have taken here 2L from the origin, right. So, the magnitude of the electric dipole moment, we can say that the statement which says the product of the magnitude of either charge and the distance between the two charges, right. And the direction of this charge, we can say that is negative to positive. It is from the negative to positive, the dipole we have to say. The SI unit is coulomb meter. Electric field at an axial point on an electric dipole. So, this is one of the application of the electric dipole. See, we are seeing here at an axial. See, axial point which is nothing but it is on the axis. This is minus Q plus Q. The charges are separated at a distance. So, we know that that is equal and opposite charges separated at a distance, which means what? Electric dipole. If suppose the electric field at an axial point, what it will be, we can see that you kept a point P on the axis, that means axial point on the axis separated at a distance placed in a vacuum. Now, let P be the point on the axis and the distance we have taken here R from its center O, the dipole. The side of this is the positive charge. Now, we will see the electric field due to the charge minus Q at point P. So, we have to take minus Q at point P means we have to take towards left. So, E minus Q vector which is equal to minus Q by 4 pi epsilon naught. We have to take R plus A. So, here the full value R, and you have to take from the origin, this is A and this part which is A. So, you have to take A. So, R plus A whole square into P cap. See this P cap which is nothing but the unit vector along the dipole axis from minus to plus Q. So, we can see now the plus Q part. No, so that E plus Q which is equal to, we can take that Q by 4 pi epsilon naught, here will come R minus A. So, here because we want to know about the plus Q charge, so R minus A whole square into P cap. Now, the resultant electric field for the point P. For the resultant we need to added up that. So, E vector of axial which is equal to E vector plus Q plus E vector minus Q. So, this is the resultant for the point P. By adding this 2, we will get the resultant value for that. Now, by adding that E minus Q, E plus Q, we will get Q by 4 pi epsilon naught. This value we can take it out. So, we will get 1 by R minus A whole square minus 1 by R plus A whole square into P cap. So, we will get Q by 4 pi epsilon naught into, by mathematically simplify this, 1 by A square minus 1 by B square formula you can use it. So, you will get finally 4AR whole divided by R square minus A square whole square. So, E axial value which is equal to, we will get 1 by 4 pi epsilon naught, that is what? K. So, the proportionality constant of a Coulomb's value. So, 1 by 4 pi epsilon naught we can take it out. Here we will get 2PR. How we got the 2PR? From that is P which is equal to Q into 2A. So, that we got 2PR whole divided by R square minus A square the whole square. The value of A we can neglect and we can take only the R square by explaining. After you have explaining the mathematical work, you have to do the mathematical work. So, you have to be well versed in math to know about the physics derivations clearly. Now, R square minus A square whole square you have to abbreviate it. Then you will get 2PR whole divided by R power 4. Is it right? This is A square minus B square, the whole square formula when you used. You will get R power 4. Here by simplifying R power 4 with R, you will get 2P by R cube. So, this is the value for the E axial, that is the electric field at an axial point of an electric dipole, E axial which is equal to 1 by 4 pi epsilon naught 2P by R cube into P vector. Electric field at an equatorial point of an electric dipole. Now, you are saying this is the electric dipole. You have to know about what is an equatorial point. See, the axial point which is nothing but the point which is on the axis. Equatorial point which means near the dipole. We have to consider near the dipole. Now, this is the dipole. We have taken and assumed a point near the dipole. So, we need to know about the value, the electric field of this point for this dipole. Let us see that. So, this is the distance we have taken 2A and the point OP which is equal to R we have taken. So, from origin to either one side of the charge is A, another side that is minus Q, for that A you have to take it equally, right. So, let us see that. So, we have taken that OP which is equal to what? R, right. So, now the electric field at point P, now the electric field at point P due to the charge plus Q. So, we have taken the charge due to the charge plus Q, we can take it, that is E plus Q vector which is equal to 1 by 4 pi epsilon naught Q by R plus A, that is R square plus A square. You have to take the value for this plus Q you have to take it. So, along the PA value, right. You have taken the PA value for this, right. For that minus Q electric field 1 by 4 pi epsilon naught and Q by R square plus A square. This is for the direction along with PB, this value, right. Now, you need to know about clearly the magnitudes of E minus Q and plus Q are equal, right, the magnitudes. So, you can take the E minus Q which is equal to E plus Q vector. So, that we can write that is equal to 1 by 4 pi epsilon naught into Q by R square plus A square, right. Now, you must know about the components of the E plus Q value and E minus Q value which is normal to the dipole. So, normal component will get cancelled out. So, you do not want to consider the normal component, you can take only the parallel for this point. Here the normal component, the sin theta will get cancelled out, and only you can take for that the cos theta, that is the parallel component will get added up. So, that you can take E equa, that is equatorial, which is equal to minus of E minus q cos theta plus E plus q cos theta into p vector, right. So, you will get now minus of 2E minus q cos theta p cap. So, which is equal to minus 2 into 1 by 4 pi epsilon naught into q by r square plus a square into a by root of r square plus a square into p cap. See, the value of cos theta, you have to take it, that is cos theta, which is equal to what it will come? That is a by root of r square plus a square. So, this is the value we applied here. For the cos value we applied, right. So, 2 into 1 by 4 pi epsilon naught into q by r square plus a square into a into root of r square plus a square into p cap. So, we got minus p by 4 pi epsilon naught into r square plus a square 3 by 2 into p cap. So, finally, we will get by explaining this as per the mathematical formula r square plus a square into 3 by 2, we will get only the value for that r power 4 as usual what we got for the equatorial. So, we will get 1 by 4 pi epsilon naught p by r cube only. We do not want to consider the a square value, the explanation part of the a, because it is negligible value only, it is getting the too much of higher order values. So, that we do not want to consider, only we can take the r value, right. So, the E equatorial 1 by 4 pi epsilon naught p by r cube into p cap. As we know that E axial which is equal to 2p by r cube, that is this value is k. So, k 2p by r cube into p vector, p cap, and the E equatorial is 1 by 4 pi epsilon naught into p by r cube. So, E axial which is equal to 2 times of the E equa. Now, torque on an electric dipole in a uniform electric field. Suppose an electric dipole which is held in a uniform electric field, that is the uniform lines of forces which we kept here, this is the uniform electric field. Now, we kept with an angle, it held with an angle. If suppose what it will undergoes any translatory motion or what it can produce, let us see that. See, the force PE will be acting equal and opposite to this dipole. So, what will happen? The net force will be 0, but it will produce a couple. It will produce a couple. So, that there is no translatory motion in this. It will produce a couple. The couple will produce the torque. The torque, which means what? Equivalent opposite force. It will produce equivalent opposite force. So, torque which is equal to force into perpendicular distance we can take. What is the force which is equal to here? The force PE which is acting on it, QE into 2L sin theta. So, tau which is equal to what? QE into 2L sin theta, that is the perpendicular distance. Force which is equal to Q into E. Here the Q into 2L, that is equal to P, we know that. P cross E you have to take it. So, tau vector or tau which is equal to P vector cross E vector. So, this is the torque on an electric dipole in a uniform electric field. Yes, let us recall the video. Now, we have seen that electric field. What is electric field? It is the space around the region of space around the charges and the system of charges, we can say. Electric field lines which means these are imaginary lines, right. So, what are the properties of electric field lines? So, you want to recall means you can pause the video and you can see the video again and you can conclude it. Yes. Now, the electric field lines properties, that is, they are imaginary lines and it starts from positive and ends with negative, and they do not present in nature, imaginary lines as we said before, and they do not intersect each other because there is no two directions for that. And the next one is, we have seen that electric dipole, the dipole is a pair of equal and opposite charges separated at a distance, and the application of the electric dipole, and one we have seen that axial E, which is equal to 2p by 4 pi epsilon naught r cube, and for equatorial line we have seen that E equatorial, that is electric field equatorial, which is equal to p by 4 pi epsilon naught r cube, right. What is torque? Torque on an electric dipole? Torque, which is equal to electric dipole into perpendicular distance. It's time for assessment. See the question which are present on the screen. Just read all the question, pause the video, and you can write as a test and check with the answers. Yes, question number 1. What is a dipole? What is an electric dipole? Yes, the electric dipole is a pair of equal and opposite charges separated at a distance, right. So, when does an electric dipole placed in a non-uniform electric field which is experience zero torque and non-zero force? See, suppose we are keeping the dipole which is placed at parallel. When it is at parallel, it is a non-uniform electric field. It will experience a non-uniform electric field, right. The next question is, why is it necessary that the electric fields, the electric field lines from a point charge which is placed in the vicinity of the conductor must be normal to the conductor at every point? Why it should be normal? If suppose the lines of forces or electric field lines are not normal, then what will happen? The electric field will make the electron move along the conductor, along the surface of the conductor. When it is moving along the surface of the conductor means that will be a equilibrium will not be possible. So that it should be normal to that, right. Thank you, students.